series and look at feed-forward neural networks. Now, before we go into that, I want to make two statements. What I presented to you about linear to logistic to neural networks of vector machine is just a condensed form. Normally, those of us who have taken subjects such as neural network or data mining or whatever, this is normally covered in a 6-hour lecture. So it's condensed form, and what I did is to take about 80% of the mathematics out of the equation. Okay, that's number one. Number two, somebody wanted to know all these constants that we use, like the Euler something, the E, which is 2.7 something, and then there are so many constants in mathematics. Wanted to know where do they come from? Well, there's science behind every constant. Every constant you see in mathematics, there's science behind it. I'll just show you a simple magic here that we prove that to you. This is outside of what we are doing today. Generally, when we want to talk about a circle, we make use of 2 pi r to calculate the circumference of the circle. Okay? And we know that the pi is simply 22/7, which is 3.2 something, right? The question is, where do we get that from? It's a constant in mathematics. Where do we get it from? It's simple. If I have a circle, okay, I have it like that, I build that, I build that, I build that. Look at this. This is 1, 2, 3, 4. Right? Are you following me? Okay? Now, this is the radius, right? That's the radius. That's our R, right? Now, assuming this is the platform, and that is like a ball or a ring that I'm rolling. Okay, I'm rolling it. When I keep on rolling this, let's call this place P. Okay? When I keep on rolling this, I roll it here, roll it there, roll it there. This point, we roll, we come back to this level at approximately 3.2. Are you with me? Assuming this is my ball. I mark that point and I roll it the first time, you get in there, roll it the second time, you get in there, but that point will not come back to this horizontal level until it reaches approximately 3.2. That's where your pi came from. You choose whatever size, it doesn't matter. Let's make it bigger. Bigger size, that's it. Make it bigger size. 1, 2, 3, 4. Pick the point here. Roll it. It will come to rest. The same point will come back here at approximately 3.2. And even if it is smaller, it doesn't matter. That's it. 1, 2, 3, 4. Pick a point, roll it. That point will come to rest at approximately 3.2. That's your pi. So every constant you see in science, in mathematics especially, has a science behind it. It's not just a random number. It can be proven. And that's for pi. And it's as simple as that. So any constant you see, you are given the value. Even if you don't like mathematics, just use it. No, it's not a magic. It's not just dropping from anywhere. It has a science behind it. And the science is simple. But we don't have time to go into that. So let's come back to feed-forward neural net. Okay. Now, I'm going to whet your appetite. Why deep learning? You see, the word deep learning is exotic. Everybody likes to use deep learning. The question is, what is deep learning? Deep learning is simply neural nets. That's all. It's neural net. Now, why do we call it deep learning? We call it deep learning to differentiate it from the simple machine learning approach where you use neural network with very few intermediate level. In deep learning, you have a lot of intermediate level. In other words, it's applying neural network upon neural network upon neural network upon neural network. That's it. So deep learning is simply means neural nets. That's all. There's no magic there. That's what it means. Okay? So the question is, why deep learning? Deep learning is important when we talk about natural language processing, for example, or we talk about signal processing, speech recognition, computer vision, all the research that is going on now in what we call biomedical engineering in terms of medical devices and everything, medical imaging, and so on and so forth, is possible simply because of deep learning. Okay? So, and the reason for that is that it allows you to be able to do certain things that you cannot do otherwise with ordinary basic neural network or support vector machine or any other machine learning. Deep learning allows you to do that. But it comes with a cost. Okay? And before we talk about the cost, we can actually view machine learning into three different approaches. There's the classical machine learning techniques, and we use this to make prediction directly from the set of features. We can make prediction directly from the set of features. There's the second type, which is representation learning technique, which of course transform the features into intermediate representation before you can then make a prediction. And then the last one is what we call deep learning techniques. It's the same thing as representation learning, but here the transformation is multiple level, multiple steps of transformation. It's no more a single intermediate transformation, it's now a multiple transformation. And that's why we call it deep learning. That's all. So the phrase deep learning is not something really out of the blue. It simply says it's a transformation, a representational learning, but with multiple transformation steps. Okay? Good. Now, the renaissance of deep learning actually started around 2012. It's very recent. The explosion in deep learning is 2012. And it came basically when a competition was launched by NIST. It's a United States institute, okay? And that competition was, you have two of them, actually there's about 5 of them because you have 2 others in Asia. There's the ImageNet Large-Scale Visual Recognition Challenge. It's been there forever, but in terms of processing, the percentage error level was still very high. And the whole idea is, how can we reduce that error level? Okay? And the other challenge is what we call label faces in the wild evaluation. That is based basically on when you see an animal from a distance, and you recognize it from the facial and say this animal is this or is that. Something like that. Okay? So, and the whole idea is to reduce the error. Number 2, the advent of GPU. Okay? All majority of the computer we use is CPU, and the capacity is limited. Theoretically, in computer architecture research, you can go to any level, but CPU actually has a limited capacity in terms of practical application, and it can take you forever to do certain things. But now that we have GPU, the graphic processing unit, which of course more or less quadruple the capacity in terms of processor, then we can do a lot of fanciful things. Otherwise, deep learning doesn't make sense. Okay? So, number 3, in mathematics, remember I told you it's about vector space. So, it's about graph, and it's complex. The introduction of tensors, which now allow you to be able to process multi-dimensional arrays. Okay? Now, help us to be able to do a lot of deep learning. Okay? And that is where you get the language platform called TensorFlow, developed by Google. TensorFlow, which is a plugin for Python and C++. You can download it. Okay? It's free. And Tensor allows you to be able to do a lot of manipulation in terms of computational graph that otherwise you cannot do before. Here we're not talking about 3 by 3, 4 by 4, 6 by 6. No. The minimum we are talking about is 22 by 22. That's the minimum. Yeah, if you are really doing deep learning, that's what we are talking about. 22 by 22. Okay? That's the most current type of deep learning in terms of application that we have, 22 by 22. And then we're not just talking about one. We're talking about n of that 22 by 22. They're going to have multiple of them. Now, the question is, in terms of modeling, how do you model that? You need a tool that allows you to be able to model that in terms of multi-dimensional array. And Tensor actually allows you to be able to generalize your matrices. It's a generalization of matrices, and you can generalize it to what we refer to arbitrary number of indices. Arbitrary number. Okay? So, one, we have research in neural net that allows us to be able to do a lot of things, to have multiple representational intermediate level. Two, we have access to GPU that we can use in terms of processor that quadruple the capacity of ordinary processor, CPU. And three, we have a mathematical concept which we can use for modeling that allows to generalize multidimensional indices into any arbitrary level. And those three put together actually is the notion of deep learning. Remove any one of them, deep learning doesn't make sense. Okay? Another thing I want to add before we go into the technical things is that you only use deep learning if you have a very big complex data. If you don't waste your time. Next week when we use Weka, I'm going to show you, we use ordinary neural network and then we use a deep learning function. And you will see that the performance doesn't improve at all because the data is small. Deep learning makes sense when the data is big enough and the training process can be done adequately, then you get good result. If the data is not big, forget it. That's why in most cases, deep learning is used in signal processing, that is speech recognition, character recognition, natural languages, string, and so on and so forth. These are complex. Okay? So it's not just I have a 300 pieces of data or 1,000 these, and then because of fanciful thing, I'm going to use deep learning, you're just wasting your time. It doesn't really, well, it may give you a result, but it may not be the best result. Okay? That's just a warning. So, again, the key development here is that evaluation of machine learning method, increased amount of data, deeper and larger network architecture, that is Tensor, and accelerating of processor, that is GPU. So those are the things that actually lead to the explosion of deep learning. Okay, so before we go into the technique, I just want to pick up this. All these things are online if you want. The NIST, Institute of Standard and Technology, United States, do have what they call MIX. It's a data mix. It's been there for a long time. It contains 60,000 training and 10,000 test instances of handwritten digits. Handwritten digit. Now, the 6,000, the 10,000 doesn't make it big. But what makes it big is that, remember, each handwritten digit is what? Is a 28 by 28. Each digit is 28 by 28 matrix. Remember, it's 0 to 255. Okay? Let me show you an example of a 7. That's a 7. That's 7. And remember, we have, for digit, we have 0 to 9, which means you have 10, right? For alphabet, we have A to Z, which is 26, right? So if I take a word such as anything, car, I have 3 things in car. So each one of them is represented like that. So for car, I have 3 of these. If I take another word that is corporation, okay? Each one of them is represented like this, and I have combination of that representing that word corporation. So when we talk about 6,000 training, what we are talking about is 6,000 pieces of that, in which case each one of them is a combination of 28 by 28 matrices, okay? And in image processing, that's normally what happens. When you convert your image into digital representation, what you end up is that. Now, before we move on, what normally is done at times is to normalize it. Instead of 28 by 28, we reduce it to something like 8 by 8 or 12 by 12 to speed up the process, okay? And that's when you hear convolutional neural network, it's a process of filtering, reducing the size to a manageable size. And then they use the word deformation. We'll see it next week. You deform it in order to reduce the size and to improve the process. Okay? So that's where the idea is coming from. But originally, it's a 28 by 28 plane. Okay? And we use the word pixel. Okay? So each one point is a pixel. So what happened with this? There's a guy called LeCun. LeCun is the father of machine learning. He was recently awarded Turing Machine Award. Turing Machine is equivalent to Nobel Prize because computer science doesn't have a Nobel Prize. Nobel Prize is given to mathematics, physics, medicine, and all that. You won't see computer science here because computer science, generally information technology is new. So the Information Technology Group, ACM, IEEE, with Microsoft, Google, and all of them, established the Turing Machine Award. In terms of prestige, it's not as prestigious as Nobel Prize, but in terms of recognition, it's the same thing. In terms of money, it's the same thing. It's around $1.something million that is given to whoever is awarded. So this guy is the father of machine learning, data mining in general. And you can see here from this example, that same data we're talking about, in 1998, this group, research group, first of all applied linear classifier, linear model that we look at, linear classifier, ordinary neural nets, which is one layer. And at the end of the day, the error level was 12%. Now, we're not talking here about the computational time. It took them weeks to actually get to the end. So we're more interested in the end result. The error rate was 12%. Then they now apply k-nearest neighbors using Euclidean distance, L2. Okay? And they reduced the error to 5%. They went on and applied 2-layer neural nets with 300 hidden units. 300 hidden units. And they reduced the error just by 0.3 to 4.3. And then they move on. After some time, the NIST Institute itself applied support vector machine, making use of Gaussian kernel Remember, we saw those kernel, making use of Gaussian kernel, and they were able to reduce the error to 1.4, which is fantastic. Fantastic. Then, this guy again pick up the same thing, and his group now apply convolutional neural net. Now, be careful. The word convolution neural net doesn't mean it's deep. Okay? At that level, it's simply convolutional neural net. It's not about deep learning. So, the difference between that and any other is that they have no distortion, but they apply level 5. That we're not talking about the even. That is, you have 5 layers of convolutional neural network. We're not talking about the hidden layer. Each one of them has their own hidden layer, and then you have 5 of that. Okay? And they reduce it further to 0.95. And it stayed there. No progress. Nobody can actually make it better until 2002, when this group applied a different support vector machine, and now they are making use of polynomial. Also, they are applying what we call jitter, not just convolutionally, in terms of filtering. They applied another technique on it, and then they brought it down to 0.56. And then another group pick up from them and apply convolutional neural net, now with elastic distortion. At this point, there was no distortion. That is, the image was not distorted. But here, they apply elastic distortion. In other words, the plain language here is that instead of the image being clear, they reduce the clarity by distorting the image. That's the plain language for it. Okay? And they improve the accuracy by reducing the error to 0.4. And of course, that remained again for a long time until 6-layer feed-forward neural net, now using GPU, not CPU. GPU was performed, and retaining elastic distortion, then they improved by 0.05. Okay? Then, from there, we now move to the advent of deep learning, which is 2012. And then deep convolutional neural network, retaining elastic distortion, still, you cannot improve it. Until you have a committee of 35 convolutional neural network. That is, different convolutional neural network, committee of 35, then you are able to improve it to 0.23. And that's what is in top today. Okay? So, that explosion, for the fact that you can actually bring something to 99.77 accuracy, is wonderful. It opened the eyes of everybody to the idea of deep learning. And that was 2012. And then newspaper, CNN, television, they started carrying all the news. And then everybody gets interested in deep learning. And so here we are today. We're talking about deep learning. Okay? So, I just want to whet your appetite. The reason for deep learning, it's not just because I want to do fanciful things. It's simply, we want to increase the accuracy of prediction by reducing the error margin. In other words, we want to minimize the error and maximize the prediction. And then, because we have big data, big, really big, then deep learning makes sense. Okay? So, as an example, this is figure 7. As I said before, the 0 represent white, the 255 represent black, and the number in between represents shade of green. Okay? And that's all that you have in terms of any image, by whatever name. That's what you have. You have pixel, and you have between 0 and 255. Even if if you pick up an X-ray, when the X-ray is converted to digital representation, that's what you have. 0 to 255. I'm calling pixel. 0 is where there's nothing. 255 is where there's definitely something. In between, there's something. The in-between is the most difficult to interpret, and that's where cancer prediction becomes very difficult. Because cancer is based on marker, and marker is based on coloring. And the more deep the marker is, the more the probability that you can actually predict a type of cancer. In which case, the closer you are to 255 in terms of certain region of tissue, the likelihood it is that there's a cancerous cell. Not only that, because they are different cancer, prostate cancer is different from breast cancer, and so on and so forth, they have different shade to them. And then, in terms of predicting what is going to happen, it's just rendered into 0 to 255 in terms of pixel. So that's what you have here. And what normally happens is that in order for you to be able to process the image, you need to apply certain principle. That's where the word convolution comes in. It's a filtering technique. Also, you may need to distort. When I write my 7 doesn't appear like this. Okay? My 7 appear too clear. But when you now convert it to digital form, it may be too big in terms of data point to handle. So you need to filter it, you need to distort it, and in order to reduce the dimension to be able to process it. So that's where all those things comes from. So next week when we talk about convolution, we'll come back to that. So now that we have whet your appetite, let's go back to our perceptron. You remember that? Talk about that. So the earliest machine learning is what we call binary classification problem. And that is what we call perceptron. And that is given in figure 1.3. And this can actually be compared to a typical neuron in biological system. When you pick up a neuron biological system, this is what you see under the microscope, okay? And then when you look at that, it has dendrites. That is the input, dendrite. It has a cell body, and that's the cell body in the center here. And it has what we call the output, which we call the axon, the output, okay? So the notion of neural net, that is perceptron, comes from that idea. And it's a simple binary classification problem, and we refer to this as neural network. Remember, it's target class or out of target class. That's what a binary problem means. Okay? Then, mathematically, we can conceptualize this problem because that's the only thing we can process in computer. Remember, we cannot just process anything. We have to bring it to that level. We can conceptualize it, okay? We now introduce vector. A perceptron consists of vector of weights, okay? And a distinguishing weight, which we call bias. Why do we call it bias? Everything we do in classification is about error. As if we can reduce the error level to the minimum, then we have good prediction, good accuracy. Okay? And in order to do that, we need to introduce a notion of bias. And that's what we differentiate the principle. Let me explain it another way. If you have a set of data and you train a model with that data, and the only prediction you can make is anything that belongs to that data. If you get a query that doesn't belong to that data, then you cannot make a prediction. Are you following me? Which means that model that you have trained is useless. Because the purpose of prediction is to be able to get something new use your previous knowledge to be able to deduce what it is. So if your model cannot predict anything new, then the model is useless. The question is, how do we make the model to be able to predict something new? We then introduce bias. And by introducing bias, then the model can train itself to be able to actually talk about something new that is not in the training data. Okay? So that's the notion of bias. Okay? So we have a distinguished way to be able to call bias. Okay? And our perceptron now is a function which computes to 1 if this quantity is greater than 0. Remember that's our linear model. Look at this. That's our linear model. Okay? Our linear summation of our linear something plus the bias, if it computes to anything greater than 0, then it's 1. The perceptron is 1. If it is 0, then it's otherwise. Again, we come back again to our 1-0 binary classification. Okay? Now, to manipulate this in terms of mathematics, we introduce dot products so that we get rid of that. We equate that to that. So in mathematics, we do a lot of trick. So we introduce dot product, and once we replace that with that, the equation becomes this. It's easy to write. Easy to write in terms of modeling. Okay? Are you still following? Now our perceptron is that. Okay? It's equal to 1 if that is greater than 0. It's equal to 0 otherwise. That is, when you take the feature x, if it is in the target class, this should be greater than 0. If it is not, it should be any other value. Okay. Any questions so far? So we now use that idea. Remember, there is that algorithm which was written in form of English before. You remember, for perceptron. Now let's use mathematics to write the same algorithm. Same algorithm. So we now iterate. Okay? For each training example, SK, and the answer is AK. In other words, if I have a training example, if I know the label is what we call the answer key. The label, the one that predicted. If the label, that is the answer, minus perceptron is equal to 0, we'll continue with this process. If not, we make all the weights, that is, we calculate the difference in weight, multiply it by xi. You remember the willow thing, multiplicative, multiply it by xi, and then we go back. What are we saying here? If the difference between the label and the feature is 0, it means that we've predicted the feature. In other words, we predicted the query. There's nothing to do. But if it is different, then we need to change our weight and add that weight to the feature and go again and evaluate. That's it. You do that over and over and over and over. If you have a billion data points, you do it a billion more times, and then you end up with that. Okay? Now, that is good. Please. Yes.
Referring to 2A2.
Yeah.
The equation. Are we, in essence, trying to calculate the error that results from the deduction of the label from input?
Yes and no. What we are trying to do is actually to, we know that the target, that is the perceptron, is different from the label. That's why we come here. Now, how do we now pick up that target? We want to make sure that we can reduce the error and see whether it will get closer to the label. That's what we are doing here. Okay? You see, the problem at times is that at this point, for the fact that this perceptron is different from that, remember, the perceptron here is not just simply the feature itself. You need to go back here. It's more than that. It's actually this computation. Okay? Is this computation? Is the bias plus the feature multiplied by the weight. That's what we are comparing. It's not exactly the feature itself. So, for the fact that it's not equal doesn't mean that we throw it away, that is wrong. We change the weight to see if we change the weight, can it be closer to the label? And changing the weight means that we are minimizing the error. So how far can we go in minimizing the error depends on other things, which we'll see later on. This is not just it. This is just one of it. Okay? We may end up at a situation whereby we cannot get closer enough to AK, and we still have to interpret the other one to be 0, to be otherwise, outside of the target class. But when we add the output of that to a different function, can we bring it back close enough to the hyperplane so that we can interpret it? So that's what is going on here. Okay? So, yeah. Again, the key word here is approximation. Approximation is the key word. Because what we are trying to do here, especially when we introduce the change in weight, what we are trying to do is to approximate. Okay? So, machine learning generally is characterized by approximation. Okay? So now that's for a binary level. But binary level is only useful for certain things. It's not useful for general class. So we have multi-class problem. And for multi-class problem, we simply generalize the perceptron whereby we have multiple levels. Okay? And this is where you have the so-called hidden layers. Okay? Are you following me? So now you have each one. What we had before is simply that going into one point. Now we have more layer. And that's our multi-class decision making. So how do we deal with that? Each one of these is trained separately with the same algorithm, i.e. neural networks. Results are calculated and the maximum is chosen. The maximum is chosen. That's what happened with multiple hidden layers. Maximum is chosen. Okay? Now, when you now have the result of the maximum, the result that is produced here at times may not be probabilistic. Probabilistic in the sense that if it is 1, you know how to interpret it. If it is 0, you know how to interpret it, but in between, you don't know. So you need to feed this result into something else to make it probabilistic so that you can interpret it effectively. And that's what leads us to what we refer to as loss function. What is loss function? Simple. Coming back to your question here. Loss function is to determine an outcome, that is, how bad the outcome is. Why is it that we are not using how good? No. In classification, it's question of error, mistake. And it's how far you can reduce that error. The less the error, the less is how bad, the better the fit. So a loss function is just a measure of how bad the outcome is. Okay? So for perceptron, the loss function is 0 if the training example is correct. In other words, there's no error. No, there may be error, but the error is minimized. And the loss function is 0. It is 1 if it is correct. If it is incorrect, sorry. And then we call this a 0-1 loss. Now there's a problem in that. When it was introduced, it was beautiful. Everybody was able to use it, but that doesn't improve the accuracy much. Because if it is 1, I know what it is. If it is 0, I know what it is. So if the loss function is 0, I know it's correct. If it is 1, I know it's incorrect. What happened in between? Remember, we are still coming back to the 0, 1, 0, 1 all the time. What happened if it is 0.6? So, and because of that, the 0, 1 function worked for some time, but it doesn't work very well when you have gradient descent. Gradient descent means that you start and then you have that reduction and go, gradient descent. And then in gradient descent, you have learning parameter which is normally defined according to this rule. Okay? And if this rule is going to be useful, it cannot just be interpreted as a 0-1 result. It has to be something that is differentiable. Calculus. Differentiation. You should be able to differentiate. Okay? So if we can differentiate that equation 1.4, then we can get to a point whereby we can actually interpret not just 0 or 1, but in between. Okay? That's the purpose of differentiation. You remember our calculus? Hello? Good. Thank you. So, and then the standard loss function, for those of us who have been programming, doing simulation, whether in MATLAB or whatever, they call it cross-entropy loss function. Okay? Cross-entropy loss function is the standard function. So let's talk about cross-entropy first. Now, what happens is that we get that result. Remember, each of these is trained. Each one is trained. And then we take the maximum. And then we need to pass that result to our loss function. And the reason why we are doing that is to do what? To be able to see how bad the outcome is, so that we can interpret it, how bad the outcome is. So pass it, and then the standard one that is generally used is called soft mass. A soft mass equation is simply that. You can see that E again coming up. You don't need to memorize anything. Soft mass, okay? So what happened here is that the network is changed so that the outputs are probability distribution over classes. Okay? Probability distribution. So now when you have probability distribution now, we know that if something is 0.6, that 0.6 tends towards 1. It's far away from 0. And we can interpret that. That's the whole purpose of introducing that particular loss function. So an example here is soft mass. There are other things that you can use, but we'll get to that later on. Okay? So soft mass here is guaranteed to return a probability distribution. Why? Even if x is negative, e raised to power x will return positive. You remember that? It's possible we get a negative thing, but that we cannot interpret. So when we pass it through the soft mass, the e raised to power x will return a positive value, which will be within probability distribution, which can be interpreted. Okay? So that's soft mass. Now, what I want to do here, there's a little bit of mathematics here. How do we introduce this? Okay, no problem. You remember the logistic function we talked about? Now, picture that, plug it into this. It's the same logistic function that is being manipulated here. And when you plug it into that, you have what we call a cross-entropy loss function, which of course comes to more or less a graph like this. And it's a negative logarithm over the attribute set. And because of this curve, if the value is anywhere here in the negative zone, and you put it back into that equation, it will return for you a positive probability, because e raised to power n, okay, other than 0, will actually give you a positive value. That's all I want to say for now. Forget about the rest of the mathematics. We'll come to that later on. Actually, we are there now.
Probably you make them to stand up a bit to stretch their body and sit back.
No, it's a simple mathematics. I will show you this. The reason why I'm going to show you this, I wanted to remove all this slide and just gloss over it. Now, the reason why I want to show you is that when he is doing the simulation, probably this afternoon or next week afternoon, you will see that he's going to make use of certain function, called certain function, in the simulation. Normally, the word we use general word like simulation. Actually, what he's trying to do is to build a model. He's building a model, whether it's LSTM or it's convolutional or simply neural network. He's building it so that you can use that model for simulation. And what he's going to do is to call certain function, and those functions actually depends on certain things. They may not be written exactly this way in MATLAB, but depends on this type of equation. That's what okay? So that's why I left this first slide here, and I'm going to make it as simple as follows. This equation, we've seen it, okay? We've seen this equation, remember the softmax function, and this equation is not new to us, it's our linear model. Are you following me? There's nothing new here. It's the bias plus the feature multiplied by the weight. Simply a linear model. What is changing here are the subscripts, using J or I or whatever. It's the same thing. Okay? Now, we said this. Remember this big thing here? The L here is the learning rate. And for that quantity to be useful, we have to be able to differentiate it. It has to be a differentiable function. So we want to see here, can we do that effectively? Okay? So the first thing is to introduce this. Let me do this step by step. There's a trick we play in mathematics that at times may be difficult. You see this quantity on the left, are you seeing it? It's a partial derivative of that. Are you following me? Okay? Now, I equate it to be this. If you cancel this out, you get what is on the left. Are you with me? But I included that because I want to be able to introduce 1.11 into the differentiation. So by introducing the derivative of Lj into the equation in the upper and the lower level, we allow me now to be able to divide these into two and handle them individually. Are you following? If you don't know, but this is logic, okay? I handle them individually. So let's move on to the next one. Look at this here. See that? Let's go back. It is, where's my marker? It is this. Are you with me? So I take the left. I play around with the left. This is the same thing as differentiating that. Okay? Let's go back. What is Lj? Is that. Are you with me? I simply plug in that into it. Now, I remove the dot product. Remember, we introduced the dot product. I remove the dot product so that we can show the quantity. And I know from linear model, okay, if you apply a partial differentiation to that quantity, it should give you W0. And we said W0 is what? 1. We initialize it to 1. Remember what we did before we get to deep learning? We make it 1. So the result of differentiating that quantity should give us 1. So that's the first step. The second step, let's go back again. Look at this side of the equation, this one. I pick it up, that's it there. Okay? Are you with me? Great. Now, I perform the same trick as I performed before. I introduce this and this. Up and if you remove those two, you get your left-hand side back. Are you with me? We do this in calculus a lot. It's part of what we call chain rule, if you remember your elementary calculus. Okay? I introduce that. Why did I do that? Let's go back again. Because I have this quantity here, equation 1.10, and I want to introduce that into the differentiation. Okay? Are you with me? Just follow. Even if you don't like it, just follow. Okay, I introduce that. Now, I can play around with this. The first thing I will do is to take this quantity. Okay, sorry, my pen is misbehaving. And play around with that. And that quantity is what? Let's go back again. Look at this here. Is that? No, sorry. There's a quantity here which is PA. So I introduce that into that. And if I do partial differentiation on logarithm of PA, the result I get is 1 over PA. Okay? Are you following? Now, I come back and pick the second one here. The second one here. And I put it here. Okay? And that is it there. Okay? And if I perform partial differentiation on that, which of course is defined there, what I get is equal to 1 minus pj PA if A is equal to J. Is equal to minus pj PA if A is different from J. Now, if you don't understand how that comes, don't worry. Just follow the process. Forget about why that is that, okay? So, that's what I have there. Now, you remember this quantity. Where is it coming from? Let's go back. I'll show you where it's coming from. Can you see it there? Here. You know that quantity? So we now pick it back and then substitute what we've done before. Remember, what we did before is, okay, I have a problem here. So what we did before is to differentiating this, we know is 1. Differentiating this is we know is that. And doing this, we know is that. So we substitute all back into the equation. 1 multiplied by anything is that thing. So we don't need to show the 1. Are you with me? So we pick that and we pick these 2. And then we just work it out and it gives us this, which is neat. Okay? And since it gave us that, so we go back to the original equation 1.4, this one, and which is a derivative of that. We've shown that by applying successive derivative, that is differentiation into it, we can actually show that the difference in the bias can be the function of the softmax, okay, depending on why A equal to J or A is different from J. And then we have successfully shown that we can actually differentiate that quantity. Why is this possible? I will tell you why is this important. I'll tell you why. Look at this algorithm. We go back to our perceptron algorithm, which allows us to do a simple binary feed-forward type of thing. Now we generalize that into a multi-class training thing, prediction, and then to be able to do that, we can now plug in this equation to do what we call feed-forward neural nets. And feed-forward neural net consists of 2 things: forward pass and backward pass. What is the forward pass? The forward pass are equation 1.9, 1.10, 1.11. And those equations are these ones. That's your forward pass. Okay? There's a backward pass, which of course are equation 1.22, 1.19, and 1.14. That's the backward pass. So if you are going to write program, forget about Simulink or Weka or whatever it is. Forget about any tool. You are going to sit down and write your own program to do this. What you are going to write is actually program those equations. That's all. So what Simulink MATLAB does for you now is to provide you with functions that can do the forward, and there are different functions, and provide you with functions that can do the backward pass, and then you get your feed-forward neural nets. Are you with me? Yes. So if you forget about all the mathematics, the reason why you can use some of these functions, even when you are using TensorFlow in Python, whether it's ported on Python or C++, what you are doing simply is you are picking up library routine functions and you are using them in your program to be able to do this thing. That's all. Nothing more than that. That's all you are doing. And for you to be able to appreciate that programming, you need to be able to see why that is so. Why that feed forward is done that way. And it's done that way because of the entropy loss in terms of the software function is you can differentiate it, it's partially differentiable, and because of that you can actually separate the function. Another word for that is that you can divide and conquer. As it is in one quantity there, you cannot do anything with it. It's not useful. Empirically, you cannot do anything. But if you succeeded in differentiating it and bringing it to a certain level, then you can actually do a divide and conquer and put it together into that form. Okay, so that's that something. One other thing which I've said before is that everything in feed-forward neural net is reduced to manipulation of matrices. That's our tensor. Multi-dimensional layers, okay? It's represented that. And for those of us who have forgotten our matrices, I just took a simple example here. If I have these three matrices and I want to manipulate them, multiply the first one by the second one, add the result of the third one, it's simply doing this first step, which generates that result, okay? If we have forgotten, that is 1 multiplied by 1 plus 2 multiplied by 4 give you 9. 1 multiplied by 2 plus 2 multiplied by 5 give you 12. 1 multiplied by 3 plus 2 multiplied by 6 give you 15. That's the result of that step. Plus this. Add this together and get that. That's the way, that's why it's easy when you are dealing with matrices. You can do a lot of things really easily, okay? Because it's vector space, okay? So now what we do now, generally in machine learning, is actually to use symbol to represent that. The X here is a matrix. The W is also a matrix. The B, if you have a lot of bias, is also a matrix. And the result you come up with is a matrix. That's all. It's as simple as that. And you can then manipulate your matrices with anything as you want. Okay? So that's what you have in matrices. Another thing that you need to know is that we can also transpose matrices. If you remember, you can transpose. If you look at these, x11, x12, it's that way, it's this way here. That's what we call transpose. You can transpose matrices. Okay? Now that you know that, then let's go into the neural network now. One thing, you remember when I was talking to you, I made mention of something called empirical. Let me see if I have it there. Empirical in neural network. Anybody remember that? Empirical. Okay? Now, why empirical? There's what we call losses. Remember the loss function? There's what we call regularization. Okay? Okay? Now, when you pick up logistic regression, you can view logistic regression as a simple neural network with no hidden unit. Are you still following? Logistic regression is a simple neural network with no hidden unit, but that is not useful for us. Okay? Now, we have to have an underlying optimization criteria that allow us to be able to actually label the features. Labeling means that when I look at a feature, it has a prediction, which we call the answer. That's what we call label. And to be able to label that, we want to be able to measure how bad is the loss. And if we are going to measure how bad is the loss, we need to have to regularize it. So we can put the two together, okay? We can put the two together in one equation. And if you look at it clearly, for those of us who love mathematics, if you look at this equation, on the left is what we call the entropy. Entropy. That's all. Forget about all the symbol. It's entropy. Plus the activation function. And then we have that. Okay? And that is our regularizer. Okay? The right hand side is our regularizer. The left hand side is the log likelihood, which means the loss. So we bring the two together. So the loss gives us how bad. The regularizer helps us to improve, to reduce, in other words, to reduce how bad it is. And we put them together in one equation. And that equation now is what is used in neural network, and we call it empirical risk minimization. Empirical risk minimization. Look at what is in here. It's exactly the same equation as that. The only difference now is that we are trying to minimize that. In other words, we are averaging it out and looking for the minimum. And that is our empirical risk minimization. And this is what is used in neural network to improve the accuracy. Forget about mathematics, let me come back again. The loss measure how bad. The regularizer helps us to improve, that is to reduce how bad it is. And then we put these two together into an empirical risk minimization. Because what do we call it? Risk. If the error is too big, then there's a risk. The risk becomes bigger. If you can reduce the error, then you can reduce the risk. So it's called empirical risk minimization. Are you with me? Now, what's the difference between this and support vector machine? I want to take you back. Support vector machine use what we call structural risk minimization. What's the difference between them? Empirical is that hyperplane. Support vector machine, which is structural, is the boundary. It's a structure thing. So the calculation for structural risk minimization is more complex than this, but it includes this, plus other things. So now in a neural network that apply weight decay, instead of using just empirical risk minimization, it uses structural risk minimization. So when you hear somebody telling you he or she is using neural network with weight decay, perceptron with weight decay, what they are telling you is that instead of employing empirical risk minimization, they are employing structural risk minimization. That's all. That's just the difference. Okay? So now we can move on and introduce ourselves to deep learning. We've done with mathematics. Okay? So what we have here. Oh my, I will soon finish. First of all, there are common loss functions that you use when you are programming your lab, MATLAB or whatever it is, or anything you are programming. I'll just give you, there's the name, the mathematical name. We have what we call square error, we have cross entropy, we have submass. The distribution name, i.e. in MATLAB, would be Gaussian. Gaussian is the same thing as square error. Bernoulli, or what is called Bend function, is actually cross entropy. Discrete or categorical function is also called CAT. It's actually softmax. That's the distribution name. Okay? What do they output? The output function from them for Gaussian is this, for cross entropy is that, and for softmax is that. Forget about the formula of the output different thing. But everything they output is back into making the output a probability distribution. You can see it. It's exponential. It's exponential. It's exponential. It's exponential. That's all. The whole purpose is to make it a probability distribution. The only difference between them is that in terms of the problem, what works best? Is it the Gaussian? Is it the Bend? Is it the CAT? So if you are dealing with discrete or categorical data, your best bet would be to first of all apply softmax, which is the categorical one, and see how it performs. If you are dealing with any other thing, you can choose between Bend and Gaussian to do your something. So that's the loss function for neural network. Aha. So now what is deep learning? So this is where we stop for today, and it's a good way to stop. When we are now talking about deep learning, what is it? Deep learning is simply neural network, okay, with n number of even layers in which each one of them is also a neural network. That's deep learning. Let me pick an example here. Look at the inner layer here. Look at this one. Okay? Now, look at this equation here. Are you with me? Yes. Look at that. Replace the L with 1. A1 for the feature X is equal to W1 multiplied by the feature multiplied by the bias plus the bias. So each one of these is that. Now remember, X is a matrix, B is a matrix, W is a matrix. So this is computed, and the result of that is stored in this function H. Okay? The result of that is stored in H1. So the next time around, A2 will now be equal to W2. Okay? Are you with me? Then here you will have H1 plus B2. Now remember, H1 is also a matrix. It's the result of a computation. It's a matrix. So now the next one will be calculated, and then you have the result for the next one, and that result is stored in H2. And then you have another one. That is what we call deep learning. That's all. It's a sequence of neural net computation. And the word deep comes from the fact that you have so many layers. That's all. Nothing more than that. Okay? So our feed forward, deep feed forward, is simply a representation similar to what we have there, in which case you have the hidden layers, but the difference here, comparing to Bayesian networks, which are non-deterministic, in this case, each of these intermediate something are deterministic computations. They are deterministic. In other words, they are not just variable, whereby you can choose in between. They are deterministic computation, each one of them. And that's what differentiates a deep forward neural network from a Bayesian network, which is generally used in statistics. Okay? The whole idea is similar, but this is deterministic computation. Okay? Good. So now that we know what a deep network is, deep neural net, that's a topology, deep learning is, okay? What we are going to do next week is that we're now going to take this idea and first of all apply it to image processing, which we call convolutional neural network. Okay? And then we're going to look at Weka example, introduce you to Weka, and then we move on from there. The practical guy is sitting there, so he's going to do a lot of simulation with you. Thank you. By the way, somebody asked me whether the slide is available. Yes. I think it's given it to Dr. Du. So if you don't receive it from her, just send email to her. It's a lot of slides. What I did is to reduce it to a PDF and 4 slides per page. So even if you want to print it out, you're not printing a lot of pages. Okay? So you can get it from her. And probably what I will try to do next week, if I can finish the slide for next week on time, is to dance before the class, something like that. Maybe it will be better. Okay, thank you. And it's time for food, I think.